Welcome to the Consulting Specifying Engineer webcast, Critical Power, Motors, Variable Frequency Drives, and Variable Speed Drives, sponsored by ASCO Power Technologies. I'm your moderator, Jack Smith, with Consulting Specifying Engineer and CFE Media. Here is a list of learning objectives for today's webcast. We'll cover these in today's presentation. I'm happy to introduce today's distinguished speakers, John Yoon and Kenneth Lavorne. John Yoon is the Senior Staff Electrical Engineer for McGuire Engineers in Chicago. He has 20 years of experience in design of electrical distribution systems, and his project experience covers a broad spectrum, including high-rise building infrastructure, renewal programs, tenant build-outs, mission-critical data centers, good manufacturing practice, clean room facilities, industrial facilities. And John is a member of the Consulting Specifying Engineer Editorial Advisory Board. Kenneth Lavorne, Consulting Specifying Engineer Editorial Advisory Board member emeritus, is the President and Chief Engineer of Lavorne Engineering Associates in Pittsburgh. Ken has more than 30 years of progressive design and engineering management experience with architect engineers, consulting engineers designing electrical systems. His work designs include single-family and high-rise residential, light industrial facilities, office buildings, institutional facilities, including renovations and new facilities for hospitals, K-12 schools, and higher education facilities. Thank you, John and Ken, for joining us today. And John, you are our first speaker, and the floor is all yours.
Thank you, Jack. Let's start out at the very beginning. As engineers, we typically focus on the functionality and cost of systems that we design. Our designs are intended to provide engineered solutions to particular problems. However, relatively recently, we're seeing an ever-increasing emphasis on energy efficiency in our designs, and that emphasis is being dictated by the codes and standards that we're required to follow in our design. The use of VFDs more or less becomes a de facto requirement based on the most current energy conservation codes. So before we begin, let's ask a basic question. How did we get to this point where energy conservation is such a great driving force? To give us perspective on where energy conservation is going, we have to understand where we came from. The codes and standards are typically the result of reactionary responses to specific events. On this slide, we have three major world events that resulted in major federal energy efficiency legislation. We have the OPEC oil embargo of the early 1970s, which resulted in the granddaddy of all energy conservation codes, the Energy Policy and Conservation Act of 1975, which laid the groundwork for everything that came after it. Then after the first Gulf War, we have EPACT 1992, which basically was the inception point for the incorporation of ASHRAE 90.1 into most of our state model building codes. And then following that, we had the second Gulf War, which resulted in subsequent additional requirements that affected manufacturers of motors and air conditioning equipment to improve the efficiency of that equipment. The Energy Independence and Security Act of 2005 and 2007. Okay, moving on to the next slide. Energy code goals. So what gives the federal government the authority to mandate energy efficiency requirements? Well, there's something that's called the United States Code. The United States Code is the codification of the general and permanent rules of the U.S. federal government. All the acts of Congress that are passed into law are included in this code. The specific section of the code that applies to energy efficiency is, as you see here, Title 24, which is titled Public Health. The basic question that you should probably have when you think of public health: why are motors and VFDs applying to public health? If you take a look, we have 4 bullet points here, and this is lifted directly from the Energy Policy and Conservation Act of 1975. These 4 bullet points are, the goals are to reduce dependence on foreign energy by increasing efficiency and promoting alternate energy sources of energy, protecting consumers through adoption of consistent standards, more reliable utility grid, and promoting economic development. The following data is a bit old, but we're using this as supporting information, why motors and VFDs are low-hanging fruit for these energy efficiency measures. The International Energy Agency performed a study back in 2011 that gives you a rough magnitude of the amount of power that motors around the world use on a yearly basis. Motors all by themselves account for 43 to 46% of global electricity consumption, 7,100 terawatt hours of electricity a year. Most of this number is represented by usage within the industrial sector. However, the commercial usage, typical buildings that we design and specify on a regular basis, still accounts for over 1,400 terawatt hours per year. And the units that we're using here, terawatts, that is 1,000 gigawatt hours of power. These are truly staggering numbers. Moving on to the next slide. So the question is, what is fair game for an energy code or standard? There's a lot of great ideas out there to save energy, but how do you prioritize and evaluate those ideas? As an engineer, you might say, well, basic functional concerns. Can I make it work? And if I can make it work, can my client afford it? Well, going back to the federal legislation side, there is a very specific set of criteria that was defined in the Energy Policy and Conservation Act of 1975. These 7 items are as follows. The first one is economic impact on manufacturers, consumers. The very first thing, can you afford the product that's being made, and can the manufacturers afford to produce it? The second one is lifetime operating costs compared to increased costs for the product. Basically, for this additional investment in this enhanced product, what is the ROI? What is the return on investment? Then there's energy savings resulting from implementation of that energy code or standard. Then there's the concept of lessening of utility or performance of products. Am I specifying something that is so exotic and so fragile that I'm somehow affecting the ability of that product to do what I need it to do? The next one is need for national energy conservation, which we talked about at the first slide. And then the final one is sort of the catch-all to sort of count for other factors that may or may not be important to us as engineers. So to put this into context, until the last 2 code revision cycles, there was never any type of regulation regarding small fractional horsepower motors from an energy conservation code standpoint, and mostly because the smaller single-phase fractional horsepower motors didn't represent an overwhelming percentage of the total power being used by motors around the world, roughly about 9%. However, we are seeing changes in the code starting in the 2013 code revision cycle, where they started mandating minimum efficiency requirements that we'll talk about later. Moving on to the next slide. So why aren't we following the most current version of the energy codes? The most current energy conservation codes out there are ASHRAE 90.1, 2016, and IECC 2018. However, if you look at the website that the DOE runs, energycodes.gov, you can see that adoption rates are way behind what the current versions of the code are. This is an excerpt, again, from the U.S. Code, Title 42, that explains what this process is and why we see that lag between the creation of the code and the adoption of the code by the local states. Basically, energy code adoption is triggered by a process called determination. Both ASHRAE 90.1 and IECC are established baseline models. Every time that a new version of either one of these codes is released, the U.S. DOE is required by law to determine if the applicable standard revisions would cost-effectively improve energy efficiency. And they have 12 months to do that. And then they issue a formal determination, and each state is required within 2 years to certify it as commercial code is in compliance with their revised standard. That doesn't necessarily mean that some states can't adopt earlier. For example, Vermont, Maryland, California all have codes that are as stringent or more stringent than the current model codes that are referenced by federal legislation. The key thing to take away from this thing is that energy codes, although they are adopted by federal legislation, they are enforced on a local level, state level. So standards, while many states are behind the curve on energy code compliance, we should also recognize that there are also standards which apply to manufacturers that sell equipment in all the states. So as a result, most equipment manufacturers are up to speed with most current standards like NEMA MG1, which we'll talk about in a bit. Moving on to standards for motors and VFDs, let's put discussions about state energy codes aside and talk about motors and VFDs specifically. There is a manufacturer's standard called NEMA MG1, which is a federally recognized manufacturer standard for AC induction motors, and it's applicable from 1 to 500 horsepower for all motors less than 600 volt. This code is the standard is updated on a regular basis. The most current version is 2016, which had relatively minor revisions. The big revisions to MG1 are attributed to, again, the big changes in Energy Efficiency Acts, EPACT, and Energy Independence and Security Act of 2007. And basically, the changes associated with the Energy Independence and Security Act of 2007 was that what was originally considered a NEMA premium efficiency motor became the de facto standard as far as minimum efficiency requirements. And again, this is mandated on a federal level for all manufacturers. And these standards are now incorporated into IECC and ASHRAE 90.1. It really doesn't matter that it's incorporated because these are also mandated on a federal level for the manufacturers. Now, in regards to efficiency standards for VFDs, there is no United States efficiency standard yet. The Air Conditioning, Heating, and Refrigeration Institute, AHRI, does have a standard for the performance rating of variable frequency drives. However, this hasn't been adopted yet by the federal government, incorporated into the U.S. code, and it's expected that you would most likely see a standard either coming out of IEEE or NEMA as far as an efficiency standard. It should be noted that in the European Union there is an efficiency standard that was created in 2013, IECC 60034-2-3. Okay, and I am moving too slow, so I will try to speed up a bit. With all the code and standard background stuff, you're probably asking yourself, when are we going to discuss VFD specifically to speed this up a bit? Well, here's the lead into it. Minimum efficiency requirements for motors is dictated by NEMA MG1, which again is incorporated into 90.1 and IECC, the two applicable energy conservation codes. And it's sort of moot because, again, this is a federal standard. It isn't mandated on a state level, it's mandated on a federal level. What is more appropriate to us as specifying engineers is that the applicable energy conservation codes have requirements for multi-speed operation under certain requirements. And 90.1 2016, the most current version, tweaked those a little bit, but they are more or less the same. Moving up to the left side, let's be upfront about this. Nowhere in 90.1 or IECC does it say that use of a VFD is mandatory. There's no prescriptive requirements. Rather, what we're seeing is a requirement for multi-speed control, which is more or less outlined here, and there's a little bit more. But rather than dive too deep into that, let's look at the basic requirements. What we're seeing is a requirement for multi-speed control, not fully modulating control, the type of control that we associate with VFDs. You can accomplish the multi-speed control requirements with a number of different methodologies. However, under certain size systems, in addition to multi-speed control, you're also required to have a certain level of efficiency of that particular system when it's operating at the reduced speed. And in most cases, the various different methodologies that you might use for like air systems, like inlet guide vanes or vane axial fans with variable pitch blades, things along those lines, typically will not meet the minimum requirements for efficiency under part load conditions. So as a result, use of VFDs become de facto in most of those types of situations. And I will hand it off to Ken now.
Okay, we talked about the codes that are mandating all of this. We can now look a little bit at where the savings actually can occur. For variable frequency drives, it is dependent upon the load. If you have a variable torque load, such as a centrifugal pump, a centrifugal fan, something like that, the load torque increases as the square of the speed, and the horsepower increases as the cube of the speed. So therefore, inversely, if you drop the speed, the torque goes down as the square, and it goes down on the horsepower as the cube of the reduction. So as an example, if you reduce the speed 50%, the full load torque is 25% of the full load. And if you reduce the speed 50%, the horsepower is now down at 12.5%. So that's a significant reduction in the horsepower required to run the load if you can reduce the speed 50%. Now, if you get a constant torque load, such as a hoist or compressor or something like that, the horsepower changes linearly with the speed. So with a constant torque situation, if you reduce the speed 50%, you reduce the horsepower 50%, not the 87.5% reduction that you get with a variable torque motor. The third instance is where you have a constant power load, and that's such as a lathe or milling machine, where the lower speed operation requires a high torque. The higher speed operation requires a low torque. So you get a constant power across the speed spectrum. So we can now look at these various torque curves. This is a variable torque load of percent torque versus percent speed. If you notice, it goes up sort of as an ellipse or part of an ellipse. And that shows you this is a square law curve showing the reduction. As you can see, at 50%, you're at about 25% torque at 50% speed. And of course, at 25% speed, you're down here at 10% torque. For the constant torque motor, oddly enough, it's a straight line when you're plotting torque versus speed. So you don't get a lot of savings. You get 50% savings if you can reduce the speed 50%. But if you only reduce the speed 10%, you only get 10% savings. Just as a sidelight, one of the side occurrences of the motor horsepower efficiencies, motors are typically, for AC integral horsepower motors, are typically in the 95 to 97% efficiency range at full load. And so really, to get even a 1% increase in efficiency is very, very expensive. So that's the reason that people are looking at alternatives to achieve more energy conservation. For the constant power loads, the horsepower is constant, and then the torque drops off as the speed reduces. So let's see here. So on a savings potential, and most of the industrial and commercial buildings use variable torque loads. So the energy reduction is proportional to the cube of the speed reduction. So it's a big, big number. For the constant torque, a few of the motors in commercial installations is constant torque. So you get some energy conservation. And then the constant power, since there's really no savings potential, it works out just as well that most of those motors are in industrial applications. Motor efficiencies. The integral horsepower motors vary from 80 to 95% efficient for loads from 25 to 100% of the loads. So say you've got a motor that's operating 25% of its full load, it's generally around 80% efficient. If the VFD is added, there are losses in the variable frequency drives of around 3% for most applications. So even though you lose 3% of your total application, you still gain because of the significant reduction on your variable torque loads. So therefore your system efficiency is increased from 92 to 97% for a load between 50 and 100%. For motor efficiency is defined as mechanical output divided by electrical output. So that's how you can calculate your system efficiency. So using VFD saves energy by matching the motor horsepower to the load and increasing the efficiency of the motor system. Just as a quick example, if you've got a 25 horsepower motor operating at 90% load or 25 kW, system operates 8,000 hours a year. At 50% of the time, this motor operates at full flow, and 50% of the time, this motor operates at 50% flow. You run through the calculations. Without the VFD, use 200,000 kilowatt hours per year for this operation. If you then go through and run the calculations for using VFD, you only use 125,000 kilowatt hours a year. So that's about $11,250 a year savings by just applying the variable frequency drive to this example. We were mentioned that variable frequency drives and variable speed drives. Variable speed drives are the general category. For DC motors, you can have variable speed drive where the speed is proportional to the DC input voltage. And variable speed drive can be electromechanical using conkle pulleys or belt drives or gears. Variable frequency drives are a special case of variable speed drives that are used for AC motors only. The motor speed is proportional to input frequency. So I think John is going to talk a little bit about the basics of variable frequency drives.
Yeah, thanks, Ken. Let's dive into the VFD basics now. Now, with traditional motor starters, we have full voltage across line starters that can be thought of as big, dumb, glorious switches. But VFDs are something more. VFDs are solid-state power conversion devices that can function as both a motor starter and a speed control. The National Electrical Code does have a section within Article 430, basically Section 10, that applies to what they call adjustable speed drives, also VFDs, that provides some level of guidance regarding their specification and installation. However, it's still pretty vague. It needs a lot more development, and we'll probably see that as the use of VFDs becomes more expansive across the entire industry. But the big takeaway from Section 10, Article 430, is that totally enclosed fan cool motors, those are fans that are cooled by a fan that's on the end of the shaft. If they operate at anything other than full speed, that fan is used for cooling. If the fan goes slower, there's less cooling air, so you have issues dissipating heat from their internal windings. So there are specific guidelines, well, not very specific, there are guidelines within the article that basically state that you have to have some level of overheating protection for that motor. In the same breath, it doesn't really state a heck of a lot about the VFD itself. Again, a VFD is a solid-state power device, and the device is currently limited by the electronics within it. So the protection requirements associated with a VFD are typically much more restrictive than across-the-line starters. Sizing your overcurrent protection for a VFD at 200% of the full load current of a motor might be fine in certain applications for across-the-line starting, where you have overload protection included in a motor starter. But when you're trying to protect a VFD, especially against inrush currents associated with transients, that typically isn't acceptable. Moving on to the next slide. VFD topology. Again, VFDs are power conversion devices. Typically, most of them that you will see are double conversion devices consisting of 3 parts. You have an input rectifier, which takes your incoming AC power and converts it to DC power. You have a DC bus where that DC power lives, and then you have the output inverter, which takes the DC voltage from that DC bus and resynthesizes a AC waveform. Now, because we're resynthesizing an AC waveform, all AC induction motors, the speed of the motor is directly dependent on the frequency of the power that you provide to it. So, for example, we have AC motor synchronous speeds, 3,600 RPM, 1,800 RPM, and all those are based on a base level frequency for North America of 60 hertz. So if we change the frequency, we can also change the speed of the motor. And again, based on what Ken was saying, if we change the speed of the motor, we can dramatically change the amount of power that that motor needs. Now, when we synthesize that waveform on the output of it, it's not a true sine wave. It's created by something called pulse width modulation. Basically what we're doing is we're taking that DC voltage, both a positive voltage and a negative voltage, and through pulse width modulation, divvying up that waveform into small chunks of equal amplitude but different time. And as a result, the average amount of power that we see is represented by the curve that you see there. You can switch the inverter off faster to improve the resolution and dynamic response of the load, but in the same breath, when you turn the switches on and off faster, you have an increased chance of damage to the motor by reflective wave phenomenon, also called EDM. Typically, you will see something called an insulated gate bipolar transistor in the inverter section due to the fact that they switch incredibly fast and they allow you to create improved resolution. Moving on to the most basic type of VFD that the vast majority of applications will see is a 6-pulse VFD. Again, in this diagram, you can see 3 distinct components. You have 3-phase power going into a rectifier section, which again takes that AC power and converts it to DC power on the DC bus. And then from the DC bus, you have another series of switches or IGBTs, which convert it back into that PWM's synthesized sine wave. In this simplified diagram, there's a lot of parts that are missing, but I should give you the basic idea of what's going on. While this diagram is a simplification, you can see that when we go on to the next slides, it is dramatically simpler than some other topologies that we'll talk about. And that leads us to why we would use a 6-pulse VFD. They're cheap, they're small, and they're efficient. Typically, for most 6-pulse VFDs, they will be wall-mounted, and they can have a much greater flexibility in where they're located. However, there is one really big drawback to this particular design, the 6-pulse design, and that drawback is harmonic distortion. They create dirty power. Basically, the harmonic distortion associated with cheaper 6-pulse VFD designs could be up to the 80% range. Even after adding mitigation like line reactors, this harmonic distortion can still be in the 30% range. The IEEE standard for harmonic distortion, it has a total harmonic distortion limit of 8%, and depending on what the percentage of overall load represented by VFDs is on an electrical service, this can be an incredible power quality issue. Moving on to the next slide, this is the next step up from a 6-pulse VFD, a 12-pulse VFD. If you squint your eyes, you can see at the bottom something that sort of looks like a 6-pulse drive at the bottom. A 12-pulse VFD is essentially 2 6-pulse VFDs grafted together. They have a common output, but you can see that there's 2 rectifier input sections connected to a 30-degree phase shift transformer. Each of the outputs of the transformer feed one of the rectifiers, which in turn are connected to the common DC bus. Because of the phase shift, instead of taking power at the top and bottom of the incoming sine wave, of the input sine wave, we can draw power 12 times for each complete sine wave. So as a result, with this phase shift of 30% between the 2 inputs to the rectifiers, we can effectively cancel certain order harmonics and reduce the overall total harmonic distortion associated with this design down to 12 to 18%. While this goes a long way towards the issue of harmonic distortion, there is a significant downside. As you can see, this is a much more complex design, and as a result, with all these additional components, the physical size is going to be bigger and the cost is going to be more. It's not unusual for a 12-pulse VFD to be twice the cost of a 6-pulse VFD with line reactors. And while we were saying that the 6-pulse VFDs are relatively small, you can wall mount them in most cases, most 12-pulse VFDs are freestanding enclosures. And in addition, they're also slightly less efficient than 6-pulse VFDs. If you go to one step further beyond it, there is the concept of an 18-pulse VFDs. So if a 12-pulse VFD is good for addressing harmonic distortion, the 18 pulse is even better. Instead of doing an input transformer that has 2 outputs, we have a 3-output transformer with a 20-degree phase shift. And that feeds 3 parallel 6-pulse rectifiers. And this draws power 18 times per each complete sine wave cycle for the 3-phase input. This is incredibly effective in addressing harmonic distortion, but you can see from the basic diagram that you're dramatically increasing the complexity of the system and you're increasing the cost even more, where it's probably in the neighborhood of at least 50% more than a standard 12-pulse design. Typically, you would only see these in super large applications, say wastewater treatment plants and the like. So 6-pulse, 12-pulse, and 18-pulse VFDs were pretty much all that you could get for a significant amount of time, but there are other emerging technologies. They're not necessarily new. They've been they've been highlighted in other industries, such as the data center industry for UPSs and the like, but we're only starting to see them in the VFD industry. The first one is an active front end. Again, this isn't a new technology. What we're doing is with the active front end, again, our biggest concern is the harmonic distortion that we're introducing by the input of the VFD back onto the source and messing up other things that are connected to that same source with dirty power. What the active front end does is sort of works similar to a concept of a noise canceling headphone. We're basically inserting equal and opposite amplitude back into the input to cancel out the harmonics that we're creating. And the performance that we can get from these is very similar to 18-pulse drives, but right now they're very expensive. There's not a heck of a lot of market penetration right now just due to the cost and complexity and the fact that most people in the mechanical industry consider VFDs to be commodity items, and unless there's serious problems with power quality, they aren't really considered. The other emerging technology is AC to AC drive, or matrix type drive. Basically, we're eliminating that double conversion step, AC to DC to AC, and going straight from AC to AC. What we have is a series of 9 switches arranged that any single of one of the 3 input phases can be connected to any of the 3 output phases. And it's also bidirectional. So we can also push power back out onto the source if we had to in regenerative applications where we're trying to slow something down or we're trying to reverse it. The total harmonic distortion associated with these designs is probably somewhere in the neighborhood of about 8%. So it is very comparable to what we expect to see out of an 18-pulse drive. However, they're unusually expensive. Just because there isn't that much market penetration. It is assumed that the price will go down as they gain additional acceptance and we see more of them delivered to the field. Cruising on, we talked about VFDs. Let's go back to motors for a bit. One of the big concerns with use of VFDs is causing damage to the motors that we're connecting to them. It's not unusual where you have a client who will say that I just installed a VFD and I fried my motor a week later. What happened? The key to remember is that although any general purpose AC induction motor can run off a VFD, the big thing that is a concern is how long will it last while it's connected to a VFD. The biggest concern that we have is called a reflected wave phenomenon, or electro-discharge machining, that destroys the bearing races in the motor that are at both ends of the shaft. So what NEMA has done to address that is created a standard for what is called an inverter duty motor. The standard is NEMA MG1 Part 31, which should not be confused with Part 30, which some vendors also state are inverter duty motors, but there's very important differences between the two. With NEMA MG1 Part 31 motors, we have an improved insulation system on the windings. We have a better lubrication system for the bearings to withstand higher operational temperatures. And again, with the fast switching IGBTs that we expect to see being used with pulse width modulation, we have the fact that they can turn on and off real quick, sort of exacerbates the reflective wave phenomenon, and you can have transients which exceed 1,000 volts. So basically what MG1 does is says that that motor has to withstand transients of 1,600 volts with a rise time of 1 millisecond. In addition, oftentimes you will see standard options such as shaft grounding rings. Again, the Part 31 standard doesn't really address mitigation of harmonics. It's just basically armor plating the motor. Things like shaft rings address the actual issue of reflective wave. Moving on to the next slide, harmonic mitigation. There are a couple of ways that we can address harmonics coming from a VFD. The first one is line reactors, and these add a characteristic impedance to the circuit to sort of soften the change in voltage when we switch on the front end switches on that rectifier. Typically, the impedance of these line reactors is either 3 or 5%. And while they do reduce the amount of harmonic distortion, they also affect the efficiency of the system. They do dissipate power because of their characteristic impedance. And typically, you can't apply one set to multiple VFDs. You have to have a set per VFD. Another way of harmonic mitigation is an active filter system. This is sort of similar to the active front-end VFD design philosophy, except it's in a separate enclosure. And then it basically inserts equal and opposite amplitude to the harmonics that you're creating by the VFD. The one benefit to this is that you can specify one filter for multiple VFDs, but just like an active front-end VFD, they are expensive. And then finally, AC to AC matrix type drives is another valid way to address harmonic mitigation in addition to 12 pulse and 18 pulse transformers. So with that introduction to the bits and pieces that we use for harmonic mitigation, Ken will talk a little bit more about the cause of harmonics.
Yeah, thank you, John. Actual cause of harmonics results from the electrical distribution system attempting to respond to the square wave from the SCR switching as they turn on and off to modulate the wave going to the motor. So since it has impedance, it can't respond instantaneously, and so therefore you get harmonics created. If you had a system that had an infinite fault duty, which doesn't exist, but if you had one, you wouldn't see any harmonics. If you ever look into harmonic issues, and I've written a couple articles in CSE that you can look up. The smaller distribution systems have much more impact from harmonics than the larger systems do. So as long as you can keep the harmonics as part of the current wave harmonics, those really don't bother anything other than maybe some wire heating or transformer heating. It's the voltage wave harmonics that are the problem. So whenever you're having them metered, you should meter for voltage wave harmonics to determine whether you have your total harmonic distortion as being for a larger or for a problem or not. So if we can look at some methods for harmonic mitigation, one of the things I've used much of the time in the past is passive harmonic filters for each VFD. The problem with applying any kind of harmonic filter on a group of VFDs for a group of motors is then the VFDs can interact with each other. You may be able to mitigate the harmonics going back into the distribution system, but then the VFDs interact with each other. Drive isolation transformers are really good for isolating motors from VFDs to prevent the reflected wave issue. Or series reactors work good, but don't try to depend on drive isolation transformers to limit your harmonic interference. Just as an example, in my office a few years ago, we had a VFD on a small machine that began operating erratically, and all of the printers in the whole building quit working. What we found was we had a 6-pulse UPS that had no input filters. It was an older uninterruptible power system, and it had no input filters at all, and none of the VFDs had any input filters. We traced the actual source of the harmonics that were creating the problem back to a failed power factor correction capacitor bank. We were able to get the capacitor bank back online, and the VFD and the printers began functioning normally again. So we found that just adding some capacitance to the distribution system actually mitigated some of the harmonics in the system. It absorbed them. So back to you, Jack. We can go to the questions.
Thank you, John, and thank you, Ken, for that excellent presentation. Okay, let's get to some of these questions. John, the first question goes to you. You discussed the need to specify inverter duty motors and related power circuit features, such as input or output reactors, in order to successfully implement VFDs in building designs?
Sure. This is a two-part question. One, we're talking about input to the VFD. So what we're addressing is power quality issues that use of the VFD may cause for all the other loads in the building. So in that particular type of situation, it's primarily based on an IEEE 519 evaluation, where you take a look at the overall transformer capacity and impedance and compare it what you're adding in terms of the existing load or other loads in the building, and comparing it to the harmonic distortion caused by the VFD. And unfortunately, there is no sure quick-fire method for doing that. Oftentimes, you need information from the manufacturer to determine what's required there. So the cop-out answer is you have to talk to your VFD manufacturer and find out what the characteristic harmonic distortion associated with their particular design is. And most of the manufacturers can do that for you. The second part of it is inverter duty rated motor. So what we're talking about is not power quality for the rest of the facility. What we're talking about is the ability to have a long life motor that isn't going to fail immediately. So what do we do to mitigate any type of issues like EDM or anything else that might cause damage and reduce life expectancy for that motor? And again, we have multiple different things that we can do. We can armor plate the motor and specify a NEMA MG1 Part 31 motor, but you can also do things to sort of mitigate the chance of that EDM. Basically, EDM is caused by an impedance mismatch between the drive, the cable that's connecting the drive to the motor, and the motor itself. And you have basically a reflective wave bouncing back and forth, increasing in amplitude every time it bounces. Well, the first thing to do is to actually decrease the length between the motor and the VFD. That helps tremendously. There's other things that you can do, like adding shaft grounding rings, which provides a low impedance path away from the bearings so you don't destroy the bearings, and there are multiple other things. Okay, let's move on to the next question.
All right. Ken, you get the next question. Could you further describe transformer isolation and passive harmonic filters? I know you touched on this, but could you elaborate a little bit more?
Yeah, thanks, Jack. The transformer isolation, I believe that the question came in on, was for drive isolation transformers. The impedance of the drive isolation transformer under harmonic applications is not great enough to actually reduce the harmonics to an acceptable level, particularly on 6-pulse VFDs. And so the way to do that is to use a passive harmonic filter. You can use active harmonic filters, but I've found that the passive harmonic filters will get you down to 5% total harmonic distortion without any real difficulty, and they're generally less expensive.
Okay, I'm going to give you one more, and this will be our last question because we're just about out of time. We have time for this one last question, and I'm going to pick on you again, Ken.
Okay.
Are VFDs worth installing for constant torque load, and will there be any significant savings?
That's a good question. For constant torque loads where the motor is significantly larger than the load, then I think using a constant VFD on a constant torque load is really a good application. But let's say, for instance, you have a motor that's 10% or 5% larger than the total load on the system. you may have trouble paying for the VFD if you only have 5 to 10% savings, since the savings is linear.
Okay, thank you, Ken. I'd like to thank our great speakers, John Yoon and Ken Lavorne, for kindly sharing their time and knowledge. I'd like to extend special thank you to our sponsors, ASCO Power Technologies, for supporting today's webcast. Finally, on behalf of Consulting Specifying Engineer and CFE Media, thanks for attending this webcast.